I'd like to say welcome. This is going to be a 7-part series called A Universe in Equilibrium, and I do hope you enjoy it. This series is broken up into 7 parts with observations. There's the Planck interaction, which is the key fundamental interaction that's taking place in the universe. We'll be talking about that at length, the first video. The second, we'll be talking about the nature of time, the equilibrium universe, a model that's developed based on the Schwarzschild and the gravitational electromagnetic equilibrium that exists. That's the source of everything. The graviton and many of the properties of the graviton. We have beyond the universe the deterministic factors which make up all of the Planckian, the quantum mechanical necessities. We'll be talking about the nature of event horizons, okay, and we'll also look at some objections to the equilibrium model, and also about the resolution of the vacuum catastrophe. There's going to be some overlap between all of these. It's essentially a single concept that repetition, there'll be some repetition. The equations are simple, and the videos will overlap. If you really want to understand, you're going to have to be looking at more than one video. It won't be enough just to see this part, the Planck interaction. You're going to want to look at the graviton. You're going to want to look at the equilibrium universe and see what the source of the Planck interaction is, and that type of stuff. Okay? We're going to start with the Planck interaction, and the first thing I'd like to say about the Planck interaction is that it represents a great gulf between matter, ordinary baryonic matter, and a final transcendent and internal event horizon. Now, this might be, how does that happen? And we're going to go there. We're on our way there. But there's this gulf between what we call normal reality and a final event horizon. This Planck interaction, it's internal and it's non-local at the same time. It's non-local because it's transcendent. It's completely out of our range. What I want to say here is that there's no measurable physical or baryonic interaction. We can't measure. It's beyond our ability to measure. Okay, so it appears to be non-local. Okay, and it occurs in a very high energy, the Planck force. Okay, and this enables it to influence everything in the universe. Okay, now it develops complex or imaginary field values that yield the holographic results. Okay, and they provide also for the stability of matter. Okay, and this all occurs through this final transcendent event horizon. We're going to be looking at evidence, symmetry, and measurements, and we're going to find that equilibrium is the basis for the stability of matter. It's equilibrium. There is an equilibrium that's taking place, an exchange that's taking place between two domains, and we're going to be looking at that in particular. We're getting now closer to really approaching the Planck interaction, and I want to ask some questions, set some context, and then we're going to dive right into the Planck interaction. And the first question is, we've all heard the phrase "let there be light," and I want to ask you, what is light, and where do the constants come from? I also want to ask, what does the existence of light and these constants imply? These constants and the existence of light itself and of all reality implies an interaction, an equilibrium interaction between different reference frames. They involve two domains, the gravitational and the electromagnetic. Okay, and these are defined through the Planck interaction. So now, one of the most telling facts is if we take the momentum of the photon, okay, whose momentum is mc, and we find that it is an exact partition, okay, of c squared. You know, you've got mc squared, and instead of mc squared, just take off, you know, 1/2, or, you know, the speed of light, okay, and so we have that we've got an interaction between two reference frames, all right? And these two reference frames, as we know, define all of energy and all of mass through the E equals mc squared equation. So looking at a little bit further on this exact partition that I've been talking about, we take a photon. Now, from its emission to its final absorption, in its own frame, according to special relativity, no time passes. All right? That's key as well. That's principle as well. We're going to show what happens, and that this time that does pass is actually a complex value. An exact partition of mass times the speed of light squared. Okay, and an interaction between two reference frames, two energy domains. Now we find that everything in the world is dominated by waves. All interactions end up being represented in waves, whether it's the electron, whether it's DNA, whether it's, you know, mass movements of the stars or of the earth or of water. It's all representable in waves. James Maxwell brought us to an understanding that you can see he derived the speed of light from the basic principles. Now, this basic principles say something about space. We're going to be talking about space in depth. And we find that the alpha constant and the phi constant all come from this same basic framework. What is space, and how are we going to define it? And we're going to go there as well. Okay, Max Planck, he looked at symmetry, at chaos, at temperature, all right, and derived the quanta, the foundation of quantum mechanics. Max Planck and Albert Einstein worked out from the Planck quantum, H, which I have here, that frequency and determines essentially the amount of energy that's involved in this space that we're all involved in together. And finally, special relativity and Einstein's equation equals mc squared, showing that mass itself is part and parcel of the same interaction. That's a universal interaction. So one of the questions is to help give more context, because these are complex, involved ideas, is the principle of the speed of light. I just some pointing out some things here. If the speed of light, for instance, were infinite, really infinite, there's no limit, then essentially there could be no reactions at all. There would be no time to have any reactions take place. And we know that reactions, they don't all happen at the same time. All right. So there, not only do we have time given to have reactions occur, but we also know that there's a certain amount of displacement. So essentially, we have a single universal nature. Time, the passage of time, is relative to the velocity of light. And we need a way to describe these displacements that are taking place. Okay, eccentricity of a circle is what was chosen by Einstein and others. All right, and all of the theory of relativity, special and general, essentially are based on this same eccentricity of the circle. And we find ourselves with an impossibility of having an absolutely fixed measure of anything, exactly because of this. And those of you who have studied relativity science will know very well what I'm talking about. Those who are new, you're going to have to study more. with slightly differing high velocities. Once you're at the high velocity, you get very slight differences and you start to see really big changes in dimensions. Okay, whether it's time, whether it's space dimensions. Okay, and the question is, how does the quantum fit into this? We've looked at a quantum. Exactly what is the source of the quantum? So one of the questions we'll be answering in this series here. So the question, do we have a minimum length, the Planck length? And does that somehow contradict general relativity? Because general relativity, you're supposed to be resolve it to an infinite, a singularity, which is this theoretical supposed infinitely small point, which has an infinitely great mass. It just goes completely against common sense, and the quantum actually helps to resolve those types of problems. We're going to be looking further at that as well, and you'll see it in the other videos. So this eccentricity that we've talked about based on the circle affects time, and according to the same equation that's used for the eccentricity of a circle, and we find that there's a relationship that exists between the velocity of light, the square of the velocity of light, and Schwarzschild radius. Okay, so we have a determined relationship between these two. And we have some more considerations that have to be looked at. One of them is, how are we going to measure things? Okay. And what is the ultimate source of this inertia, this gravity, this mass energy, and of these effects? We have this eccentric system that general and special relativity meet there, okay, at the Schwarzschild radius, and they meet there at the velocity of light. And so what exactly are we looking at here? If the electron and everything is a wave, what's waving? That's been asked by many. And we find that the nature of the space that we're in points directly at light as the speed of light. And so what's at this essence? We also have to look at something I call concurrence, okay? And that there is no reaction of any type without some type of simultaneity. There can't be. Things have to interact, and that means simultaneity. There's no way out of that. Yet each observer has his own pattern, and that depends on his trajectory, his speed, and his location. So concurrency goes directly to coherence, all right? We have no interaction without simultaneity, and there has to be some kind of description. There must be some kind of generalized simultaneity in all locations. And that is defined by the Planck interaction, which we are looking at in this video here. So we've got a universal waveform, some way of describing everything that's happening in the universe, and it represents something that's in a certain equilibrium. We have quantic availability for any of the interactions, and we have what we call free space interactions. And those are normal interactions in free space. We have symmetry, okay, the importance of symmetry. The future, the present, the past, all right, are all linked by symmetry. That's important. Needs to be looked at. It's not only a pretty slide, but it needs to be looked at. Okay, and we need to look at phi. Phi, normally. I'm living in a Latin culture, so it's phi down here. So most of us know about the Nautilus shell, the golden ratio, right? And we find it in everything, We find it all over the place. Why? Why do we find it every place? We'll actually touch on that as well. Need to be studying the NIST. And here in this NIST thing, I wanted to show you we've got the Planck mass, the Planck temperature, the Planck length, the Planck time, elementary charge, the Planck constant, Newton. All of this stuff has to be looked at. All of this stuff is interrelating, these constants and others. And we're going to need to knowing these very well. Here we are looking at particle interactions. And we see that for the wave, it's the Planck constant, and for the particle, it's more the reduced Planck constant, which generally lines up better with particle calculations. Further, I want to point out that the units for the Planck constant is joule seconds, and that's not joules divided by seconds. That's joule times seconds. Okay, so that we have energy in joule times seconds will give you the Planck constant, and in particular, that's the Planck energy times the Planck time will give you the Planck constant, reduced Planck constant. Okay, for the Planck mass, it works. It's the most used, and essentially that we have here that space-time and energy are interchangeable. It's right there, looking at us in the face. We're back to our eccentricity diagram, except for this time we're at the level of the Planck interaction. Okay, and what we find here is that at in three spatial, we've got three spatial dimensions here. Okay, the z, and we have the t, the time going. All right, and we have that at two Planck lengths here, this here Planck length and Planck length. We have there the Schwarzschild radius. I'll take another slide here that's a little bit more fun to look at here. Essentially, at two Planck lengths, we have the Schwarzschild radius for the Planck mass. And so this mass exists within its own black hole. And from there, it's unreachable. It's already non-local. Okay, can't get there because of, the rules that govern interactions with normal space and black holes. This interaction serves as a universal quantum background. Okay, so it's not what we thought it might be. It's something much more intriguing. Now, extremely high energies are happening at this Planck inflection point, and therefore it acts as a transcendent pilot wave. It's the meeting place of all interactions. Your time trajectories going in and out, and then all of our measurements come into question because we're dealing with a transcendent pilot wave, and we have to, take a look at that and figure out what's going on there, the Planck interaction. Okay, it's an event horizon. It alternates at the Planck frequency, extremely high frequency, and completely beyond our ability to measure it. But there are some things we can calculate. One of them is the fact that the Planck interaction is the only source, universal force derivation of the alpha constant comes exactly and directly out of this Planck interaction. That the ubiquitous alpha constant and its force derivation comes directly out of the Planck interaction. And I have the numbers here for you. You can see them here, and they're broken down here. The item being, the Planck mass, 1.707 Planck mass, half the Planck mass, the Schwarzschild radius for each of those, the de Broglie radius, The Coulombic force at the Schwarzschild radius, the Coulombic force at the de Broglie radius, the gravitational Schwarzschild force, and the Planck force, calculated directly from the Planck energy. And here are the ratios, and you can see we have our alpha constant appearing in different ways. And this is the only place you'll find a force derivation of the alpha constant. It's called the Planck interaction. To get a little bit closer to this idea, I wanted to focus a little bit on the Planck interaction itself. We've got the half the Planck mass, we've got 0.707 times the Planck mass, and we have the Planck mass. And we'll focus just on one of these to give you an idea how this chart works. For the Planck mass, okay, we have that the Coulombic force at the Schwarzschild radius, okay, divided by the gravitational force at that Schwarzschild radius is equal to alpha. And also for the same Planck mass, we have that the Coulombic force at the de Broglie radius divided by the Planck force, okay, is also alpha. So at every point in the universe, we have a source for the alpha constant. I'd also like to mention that the Planck force is a gravitational calculation. The number of Planck interactions in the universe is 10 to the 61st, I believe. So you'll find this interaction at every single point in the universe. You'll find this interaction governing everything. We also find at the same time that this alpha constant force derivation gives us charge. So this same interaction is the source of all charge as well. And I have the equation here for you. And it's explained here a little bit more in depth. You see that the energy of any particle times its wavelength under the charge will actually give you the alpha constant. Now, in order to have an equilibrium universe, we're going to need a symmetric source for everything. And the Planck interaction provides that. The Planck interaction effectively sits at exactly in the center point, mathematically at the center point of the major forces. I have here in yellow the Schwarzschild radius for any and all particles, and here we have the de Broglie radius for any or all particles. And you can see that they're perfectly balanced at all times. And I'll be showing you the actual another equation that shows this. Here's an equation that shows it pretty clean. We have the value, which is the Bekenstein-Hawking black hole constant, and that constant is equal to the product of the Schwarzschild radius by the de Broglie radius for any and all particles, which is also equal to 2 times the Planck length squared. All right, 2 times the Planck length squared, which it's all the same, and it is the source for all things. So we have now an unapproachable quantum interaction field, and later on I'll be looking at how many of these inflection points we have and how they serve as a point of nucleation for all of space. We have an interaction that determines everything that is, and this all from across a great gulf that we can. It's transcendent, and yet interacts with everything. It's non-local and affects everything. Charge separation, this alpha constant force derivation, gives us charge, which I started to talk about earlier. You can see we have the source of charge separation here. Now, I've calculated the number of these interaction domains, and we've got roughly 3 to the 61st domains. Those are just Planck interaction domain. And these define all the rest. And from this, we're going to be deriving all kinds of things. And it's all based on the Planck length. So, how can this be? Okay. Well, we have here a little video that I found, and it shows how the whole can interact with a source, a frequency source. Essentially, what I'm saying is we have the Planck frequency source and the middle of the universe, the internal part of the universe, and it's creating all of baryonic matter. Let's take a look at this video and see if we can't, you get an idea how this is. And you see here that we're starting to get these forms based on differing frequencies. And the man pours a little bit of sand, chladni. He's up the frequency, and so you get higher, more. And the sand points would represent accumulations of baryonic matter across the universe. Yeah? That's all based on frequency. Okay, let's go ahead and jump to the next one. Here's another version of the same thing. It's just a little bit more interesting. This is with a local focal center. And you can see how even the differing orbitals with higher frequencies, different orbitals could be developed, and the types of interactions that could prepare orbitals inside an atom, for instance. It's an interesting video. He keeps upping the frequency and the number of orbitals goes up. He finds a harmonious point there. So, and it keeps dividing up. You see, every time he ups the frequency, it starts spreading out, and off you go to another one. It's an interesting video. It shows some of the ideas that are in place. So that's it for the first video, and I hope you enjoyed it. And we'll be getting on with the other videos. And if you have any questions, please visit the site of Academia, and it's here at the bottom, listed at the bottom, and you can actually read the paper that was written that this video is derived from. Thank you very much.